Hola. It is a great pleasure for me to be here delivering this lecture commemorating the 70th birthday of Welington. In fact, when Welington arrived, I was teaching courses, but soon I was attending his seminars and learning with him. After the first course, at the end, he was challenging me with difficult problems on differential equations. So, and then at the third year, I was attending his seminars and trying to follow him. So it is a pleasure for me to be here and deliver this lecture in honor of Welington. So my subject has an abstract that was in the I will read this abstract. So principal curvature lines on a two-dimensional surface mapped into R3. And these are curves which satisfy a certain differential equation, which is called Rodriguez equation, written here as an implicit equation. But I will discuss the geometry of this equation before I get into the core of the lecture. But you know for your classical differential geometry culture that there are two types of being quadratic. This equation, it has two directions, defines two direction fields, not globally, but locally two direction fields. These direction fields break down at the singularities, which are called umbilic points. Here are the umbilic points. I will go back into the definition of this. These umbilic points are where these equations are identically satisfied. And there are one direction, which is the maximal principal direction, one of these directions, defined by the vector gamma prime, and gamma is the solution curve of this equation. So my lecture deals with the interaction between classical differential geometry and classical dynamical systems. And what is classical differential geometry? Is the geometry that you can study considering the two fundamental forms of geometry, the first and the second. You can also consider the second and the first because they commute. And what is classical dynamical systems? Is closer, the dynamical systems, a very broad area, increasing, expanding in many directions, as is also geometry, differential geometry. But classical dynamical systems is the one that is closer to Peixoto, to Andronov-Pontryagin, to Poincaré, to Welington and Jacob book. And that's what I call classical dynamical systems. So let me begin writing this equation in another language, in another form, so that we get closer to classical differential geometry. So what are we talking about? I will write it here. I will go backwards in the timeline. So I will write this equation. We have a surface, a manifold. We are considering immersions of this manifold into R3. Immersions. And this manifold is oriented. So you have a way to say when a chart is positive or negative. And this is oriented also. So principal geometry is an oriented geometry. You have orientations. And this is oriented. This means that you have a wedge product here. And so as you see, the equations written there are, you have with these two gadgets, you have the normal to the immersion. So this is an immersion. You have the abstract surface here, mapped into R3 with tangent plane and normal direction, well-defined normal direction. Locally, this normal direction is defined by d alpha, du, wedge, d alpha, dv. So this is the normalized, the unit normal direction. And so the differential equation that I'm writing here means that the derivative, you have a curve gamma here, which has a tangent vector here, and this is mapped both by the derivative of the normal. The derivative of this unitary map comes and drops here into this plane, into the tangent plane. And on the other side of the wedge, you see the derivative of alpha taking the curve in the abstract manifold into the space. So you have here a curve, and here you have the derivative of alpha. Derivative of alpha at gamma prime. So the equation means that these two vectors are collinear. That means that the wedge product of this and this, which is orthogonal to this vector, is 0. So another way to write in this equation is like gamma prime equal what? du u plus dv dv. And then you substitute this equation. You take this differential expression inside that wedge product, which is orthogonal to this. So you take the equation up in the announcement, and you scalar product with the normal. So here, this is the equation upstairs. And the scalar form of this vectorial equation, which is redundant there are three equations, but in fact it is one scalar equation only, amounts to this expression, which is a scalar expression. When you make the calculations, taking these expressions, derivatives in the frame, local frame u and v, then the writing in detail of that expression, which is this, amounts to the following expression, which you will recognize better as the equation for lines of curvature in classical differential equations book. dv squared du dv du squared e f g small e small s and small g. So this is the differential equations of lines of curvature in a chart here, uv, and here you have a way to see as a quadratic equation which is principal curvature line and which is not. So in general, this equation, which you can write also this way, I will not continue writing too many formulas because I want to have time to discuss the geometry. Because if we take this formulation of the problem of recurrent principal curvature lines and use this definition, probably we will get lost in the solution of the discovery of lines of curvature which are recurrent in the surface. No? We're going to know when a surface has this solution gamma, which comes back there and never closes. And since there are two of these equations, you may have another solution in yellow here, another, which is also recurrent. But I claim that with this formula, with this definition, it is difficult to approach this problem. So, but here I put my subject in the realm of classical geometry. But this equation, as you see, you can write in the tangent. You have m here, And here you have the projective bundle. And you have, at each point, you have two solutions, 1 and 2. And at points where these lines are collinear, when these lines are collinear, then the equation is identically satisfied. And so this is the singular point of the equation, when it is identically 0, and this is called the umbilic point of classical geometry. So this equation here defines a surface, two surfaces in the projective bundle of the surface, and this surface has lines contained inside above the umbilic points, right? And here you have two sheets here, one that we may call in green and one that we may draw in blue. And this is where you have one direction, L1, and here's another direction, L2. And these direction fields are separated in these two sheets. And so you have direction fields, which is the classical way the geometric way of posing differential equations. And so we are reading to the world of classical differential equations, classical dynamical systems, close to differential equations. As these differential equations here approach this singular line in a certain way that we will recognize as the classical objects of singularities of differential equations. So I will reach these remarks here very rhetoric at the moment, but from the point of view of historical landmarks leading to these considerations. So how is my setting of the lecture? We want to give examples of immersions with recurrent principal lines. Unless you have seen these examples with this definition, my claim is that you will not get them in an hour. But I will ask if someone found the recurrent lines of curvature only with this definition. But I will discuss the historical geometric background leading to these considerations, and then I hope it will become clear how this problem arises naturally and how they fit into something that is more familiar to the distinctive audience of this seminar, of this meeting. Okay. So I am discussing now historical background concerning classical differential geometry and the motivation leading to the very definition of these principal direction lines. And this background is concerned with great mathematicians of all time, Euler, Monge, Dupin, Poincaré, and Darboux. So this is my starting point, just to enter into the subject more geometrically and more historically. And so this is the first subject that I will discuss, these mathematicians, Euler, Monge, Dupin, Poincaré, and Darboux, and recognize, observe in the past germs or indications of a theory to study the object that I am proposing here. These equations written there. No? And then the interaction of this geometrical facts, with the classical dynamical systems. And by that, I said already what I mean classical geometry. So classical dynamical systems is Andronov, Pontryagin, Peixoto, Anosov, Pallis, and de Melo. My strategy here is to quote as many people as I can in the audience, so to prevent they to sleep. Says they will enter the here. Okay, so, and then here is just Pallis and de Melo will come just to prepare us ourselves to new flights, to leave 2 dimensions and 3 dimension space and project into higher dimensions. Ne? Here is the definition of, so here I am taking the definition, very modern definition of the 19th century given by Rodriguez, characterization of Rodriguez in the 18th century of lines of curvature. But the original fellow that defined lines of curvature, directions of principal curvature, was Euler in 1740. And here he defined it by taking normal sections, and meeting the surface in a curve, in a normal plane, and this curve, as a planar curve, has a curvature, a one-dimensional curvature. And this curvature changes with the plane, normal to the surface. And the maximal occurs at the maximal direction, and the minimal at the minimal direction. And when all directions are equal, this is the umbilic point, like in the sphere. All planes that you take, like in the plane. So this is the definition. And it's very interesting, those who are fond of history, to read the introduction of this paper of Euler, because he says that the curvature, okay, was studied, was well known, well understood in his time for 1 dimension. But for 2 dimensions, only had indications of the curvature in the works of the Greek mathematicians for very symmetric objects, like cylinders, like cones, like spheres. And even the cones had the sections, the conic sections. No? So the fact of taking, the approach, the strategy of taking the sections is something that you find in the Greeks already. But what Euler proposes in his paper is to get free of these symmetric impositions and give definitions, give concepts ready to study the curvature of any surface, no matter how it is curved in space, with the rules of calculus, differential calculus, and then this allows you to have 2 directions, and this is the definition of Euler. So by moving this point in the surface, you have a field of lines, 2 fields of lines, one maximal. So here you see one maximal and one minimal. If you orient upwards, you see that the maximal is the curve like this, and the minimal is negative like this. No? But if you orient downwards, then you change. So you have these 2 lines. The same is that you get here, but here you have to say which is maximal and minimal by making an extra calculation. No? Here you have only the lines. You took the minimality or maximality condition away. So even that, considering that Euler was a man of analysis and a man of differential equations, he didn't worry in integrating these line fields. No? These line fields of principal, he didn't worry. However, he was a man of formulae also. So he defined, he derived the Euler formula, which expresses the normal curvature in any direction in terms of a quadratic expression involving the principal curvature. So this is Euler formula, but he didn't worry in integrating these line fields, considering this differential equation. And the first one to consider the integration of this line field is Gaspard Monge in 1796, almost 50 years after Euler. No? But Gaspard Monge was also not only interested in the abstract analysis, but he was an applied mathematician, founder of the École Polytechnique in France, and the work that he proposes as a motivation for his definition of lines of curvature in this surface here, implicitly given by the ellipsoid with 3 different axes, A, B, and C, is to model the tiling of an ellipsoidal dome over an elliptic terrain. No? So you have an elliptic terrain, and so you have here the ceiling, which is and you have to put here bricks without iron. This is the era of concrete without iron. I don't know what is the specific name for this. And so there was a architecture problem in the mind of Monge. Well, anyway, he was with this motivation and the conclusions that he arrived from his mathematical study, he arrived to a lines of curvature in the ellipsoid with 3 different axes, which better than 1,000 of words, I will put a picture. This is the Monge ellipsoid, what I call the Monge ellipsoid, with the lines of curvature. Depending how you are oriented, suppose we are oriented outwards the ellipsoid, you see that the less curved are the curves going this way. These are less curved if you are in the ellipsoid, closer to 0. And if you have here, you are more curved. Ne? Depending how you orient, you get. And here you have the umbilic points, 4 umbilic points. 1, 2, 1 downwards, 1 forward. So this is the conclusion, the mathematical conclusion, and his proposal to tile, put the tiles of this building that he was planning to build along these spaces, these squares, quadrilaters, bounded by the lines of curvature. There are mathematical reasons to have this, that at the end, if I have time, I will come back. No? This is the fact that there is a mathematical theorem that was found by Monge, which says that if you take as basis a line of curvature and take the ruled surface span by a line, normal line to the surface, moving with foot moving along a line of curvature. So this line describes a surface. And then Monge proved that this line, this surface, has Gaussian curvature 0 if and only if the foot of the line moves along a line of curvature. So if it has Gaussian curvature 0, it means that two sides, 2 bricks that are adjacent, as far as they go, follow the lines of curvature, the slants of them will be surfaces which are not planar, but they are isometric to the plane, isometric among themselves. And that makes easy and possible to just glue them. In my lectures that I gave, they told me sometimes, I don't have the reference, that the ancient Peruvians, Inca architects, had also this strategy of putting the bricks, the stones, building these enormous monuments, not only in Peru, but also in Egypt, to put the pyramids standing up, no? Following this rule. No? Probably intuitively, but Monge has the proof, mathematical proof, that along a line of curvature, the normal surface is developable. It's called in geometry, it means that it has Gaussian curvature 0. It means that 2 of them can be underput together, glued together. Wow. So I get to something more theoretical now, which is this is an illustration of Dupin theorem saying that if you have a family, three families of surface, say compact ellipsoid with three different axes, like those here, like this, a copy of this, ellipsoids, hyperboloids with two sheets, and hyperboloids with one sheet. Then if two members of different families cross, no? For instance, just to be specific, the ellipsoids will cross the hyperboloids of one sheet here. Then the intersection is a line of curvature of both. So a way to find these lines discovered by Monge, by integrating by hand these equations for the ellipsoid, taken from this formula, or some equivalent to this formula, can be obtained also by implicit integration, by first integration. So because these surfaces here have an equation, and if you an algebraic equation, if you put this algebraic equation equal a constant, you are getting curves, and this is the first integral of the lines that you are wanting to integrate. No? So this is in my view, this is the first theory of for lines of curvature found in the analysis of these objects, and this corresponds to what we may call the integrable case. So this is the first indication that there is a theory for lines of curvature. Another indication that is interesting that I was happy to notice is that in this ellipsoid, in this findings of Euler, of Monge, you find elements of the qualitative theory of differential equations discovered and analyzed deeply by Poincaré. This is an example. Poincaré was a theory. And so here you have the singular points. No? You have the separatrice. Here you have this point here, this point, this umbilic point. So these are the umbilic points. We call this a D1 point. D for Darboux, that will come enter in the story later, and 1 by the separatrixes. It has only one separatrix. Each foliation, maximal and minimal, have only one separatrix. So you have separatrices, and you have connection with separatrix. No? Like a saddle connection, you find a connection of separatrices. In a certain lifting of these differential equations of lines of curvature, these connections really do resemble saddle connections. No? You have to elaborate the geometry to see this. But so this indication of the integrable case appears in Dupin theorem. Dupin theorem is about, it didn't appear here, the Dupin. Dupin is in 18, more or less. No? Now here is the architecture part in the work of Monge, the slanting of the bricks, how they must be cut to go and to fit together. And here are the planes that were drawn to show the workers how to put the bricks. No? Now we come to more advanced subjects concerning the level of analysis that we are coming into. So we have Darboux. I put Darboux and Poincaré together here. They're contemporary. And you have the Darboux theory for umbilic points. So here we have more a specific and a familiar language for people in dynamical systems, Darboux contribution can be said that he gave a description of the generic behavior of principal lines near the generic umbilic points on analytic surfaces. No? And these generic types fit into three categories: D1 that I drew here, D2 that I will show right now, and D3. So there are three types of generic umbilic points for any surface, any surface without constraints, without free to change. So these are the Darbouxian umbilics. And why is Poincaré together? Because Darboux uses the generic theory of equilibria of differential equations developed by Poincaré, the very theory that gives you the saddles and the nodes and the spiral points and the focus in differential equations in the plane. So it took some time to put these things together, and it's not so clear, these points, in the time of Darboux, because he uses very strange, that are not a la mode anymore, coordinate charts to study the umbilic points. So let me see what I am writing here. We regard Darboux as the first generic theory for local principal configurations, assimilating the local qualitative theory of Poincaré for singular points of ordinary differential equations, saddle nodes, focus, and centers. No? And here are the Darbouxian umbilics, and here is the D1 point that I draw here. D2 point is homotopic to the D1, except that this separatrix was thickened. The one-dimensional separatrix was thickening into a wedge, into a sector of separatrix reaching the umbilic. No? Not separatrix anymore. This is more like a nodal sector in the terminology of differential equations, a nodal sector, and here, yes, this is a separatrix. So a D2 is like a D1 that the one-dimensional separatrix returned into a wedge, into a sector. And D3 is completely different anymore. They are not homotopic. D3 has index minus 1/2. This has index, rotation index. Some of these resemble the configurations that appear also in the pseudo-Anosov systems. This and this. Pseudo-Anosov has restrictions of conservations of measure. Here, in this generic theory, we don't have such a restriction. And Darboux didn't have these restrictions either. So the verification of this formula for the C finite category in Darboux was for C analytic, and it was with Gutierrez that we found first these proofs for finite class of differentiability, and then more qualitative, more geometrical, and more synthetic form by Bruce and Fidal. So nowadays, we adopted the method of Bruce and Fidal when we want to explain these equations through the theory of Poincaré. So it is more clear when we're using the method of Bruce and Fidal, which is called the Lie-Cartan resolution of a singularity. No? When you have a equation of higher order, higher degree, the blow-up of Lie-Cartan shows you how to reduce, how to decrease the degree, how to separate these sheets. No? It is not so clear when using polar coordinates, as we did with Carlos Gutierrez. But anyway, this was the first proof of the theorem of Darboux with C finite of differentiability, C4 actually. And this was later. Then, how are we doing in our chronology? What is the project for today? A geometric synthesis through geometric elements that was carried out by my former student, also a professor of IMPA at a certain time, prematurely passed away in 2008. And the global study of principal cycles, for instance, here in the ellipsoid, I was mentioning the connections, the singularities, and also the cycles, the periodic orbits. All that is not a connection, nor a singularity, is a circle, a periodic circle of lines of curvature in the ellipsoid. And then we will gather this geometric information and put together following the steps of the pioneers in the structural stability of differential equations in Russia and with Peixoto. I mentioned Peixoto just to and then, so here is so this is the project for today. Just a side comment is that departing from three-dimensional ambient, going to hypersurfaces in R4, my student Garcia in IMPA made a initial study, very original and very courageous at this time, for increasing in one this dimension. Instead of taking a two-dimensional manifold, taking a three-dimensional manifold and immersing it into four-dimensional space. And looking for this structure of singularities, umbilic points. There are more variety of umbilic points, partial umbilic points of several orders. And he arrived to a Kupka-Smale class of systems. And then recently in a paper published in Jacob's journal, in the SBA, Boletim da Sociedade Brasileira de Matemática, we extended these ideas of the principal configurations of Monge for ellipsoids in R3 into ellipsoids of R4. And so this was not studied in 220 years after Monge's paper to have the complete description of the lines of curvature. You have three now in M3 immersed in R4. You have three lines, maximal, minimal, and intermediary. And so you have in this paper recently reasonably recently published in the Journal of the Brazilian Mathematical Society, also is in the archive, about these ellipsoids. And something very interesting happened here is that the singularities in this case are not points, but generically occur along closed curves. And these closed curves sort of transversally resemble the Darboux-ian umbilics, except that there are exchanges of the type along these lines when a Darboux-ian umbilic changes its type in moving along the line. So how a D1 turns into D2, how a D2 turns into D3. So here is an interesting structure. And there are also umbilic points. Natural umbilic points appear here. Natural umbilic points are the coincidence of three principal curvatures. And the description of the extension of the Darboux theorem, which describes the generic umbilic points in 2 dimensions to 1 dimension higher, is, in my view, modest view, one of the most interesting and difficult problems in this theory of principal structures. What are the real Darboux-ian points in 3 dimensions? There are 3 coincidences, and they have codimension 5. They appear only in codimension 5, this degenerate coincidence of 3 principal curvature lines. I will not have the time to talk about this. So I am reaching where? I am reaching more the subject of my lecture. So Poincaré legacy was assimilated by Andronov, Pontryagin in 1937, and further elaborated by Peixoto for surfaces in 1962. I was happy to be here in this year and learn with Mauricio the developments of his theorem, because the fact that it is not the plane but a surface is really essential for later on, came to be really essential to extend this theory of vector fields, one univalued functions, to these bivalued functions, which are the principal lines, so maximal and minimal. And then the fact that Mauricio's theorem is for surfaces really encourages a lot and makes possible to admit this as a possibility to have a theory of lines of curvature on compact surfaces, which is generic, no? Not only from the singularity point of view, but also from the periodic point of view, as the periodic leaves of the foliation, the connections, and the recurrence. No? Here we come to the recurrence. No? Because one of the Peixoto conditions is the omission of recurrences. I cannot resist to comment that since my lecture is about the interaction between classical differential geometry and the classical dynamical systems, while this classical, very important work was being done in 1937, around that, this same year, in 1938, there was an enormous work done by Elie Cartan in 4 papers around this year, studying the isoparametric immersion. What is an isoparametric immersion? It's an immersion into a Euclidean space or other more complex surface or manifold, generally with, he was taking the teoría de inmersiones isoparamétricas aquí está, en espacios de curvatura constante, ¿no? Puede ser curvatura 0, curvatura 1 como esfera, curvatura -1 como espacio hiperbólico. Entonces, ¿qué cosa es una isoparamétrica? Es que todas las curvaturas principales, todas, son constantes no pseudominio, ¿no? Están definidas fuera de singularidades en abertos y todas son constantes. Back to English, okay. Sorry. Well, then I need then more 5 minutes more. Okay, 5 minutes. Okay. Great. So this very important. This object here. So like the sphere has constant curvature. It's an extreme case. No? But these objects here are very symmetric. So here the curvature, while I mentioned that Euler was getting free of the symmetries and approaching every surface, no? Not like the Greeks approaching symmetric surfaces. Now Cartan here is going back to symmetric objects, no? With constant curvature. No? And here we are reading these papers, and I think there is an interaction, a possibility of further interaction between this work of Cartan that really is something enormously developed nowadays. This theory of isoparametric surfaces is enormously, unlike dynamical systems, this very ergodic theory, this isoparametric surfaces is something enormously growing. So we are using this as source of examples to get more complex immersions of surfaces, 3-dimensional manifolds into 4-dimensional space, for which you can find the principal configuration. The principal configuration are the foliations defined by the principal lines of curvature. So I mention this because it is a point of interaction. No? Not well acknowledged either by people in dynamical systems, neither by people in geometry. We're not aware that important things happening at the same time disjointly. No? And so here I go together again. So framework stability, structural stability, and bifurcations of lines of curvature, surfaces smoothly and algebraically immersed in R3. What do I mean by algebraically? I don't know if it's correctly written. Right. No, not correct. It's probably wrong. But because the quadratic surfaces that we are mentioned that appear in the Dupin theorem, you know everything about lines of curvature. But if you take a cubic surface, so a quadratic surface by quadratic functions, cubic surface by cubic functions, and then what are the lines of curvature of these cubic surfaces? How these lines of curvature approach infinity. So this is something that we studied with my collaborator and former student, Garcia. And it is open still, no? I mentioned that I will, to see if the cubic surfaces are closer in principal configuration to the quadratics or to the smooth case that I will go now on in my description. Here is just a pictorial artistic description of principal configurations, D3, D1, isolated principal cycles. Here is a refoliation. Here is some other configuration. It is not known whether if you give a picture in an abstract manifold, a pair of foliations, transversal foliations in an abstract manifold, a pair of foliations, transversal foliations, if this can be immersed, this is into I3, so that this immersion has these foliations of principal lines of curvature. No? This is not known. Well, here is the analytic theory of Darboux points that I will not have time to go into, but how you describe how you recognize if one umbilic is Darboxian or not. No? Here is something that I didn't touch, but here any point on a surface is described by a graph of a function. No? In degree 4, you have this description. If the second order terms are symmetric, this means that the point is umbilic. And then the coefficients that describe the Darboxian type are these first coefficients. We eliminated this type for strategic regions, and this is also possible, always possible by translations, by rotations, to eliminate one term in the quadratic system, in the quartic system. Yeah? So this term is eliminated. You have 3 terms, and in doing this strategic move, you can write really equations for the types. No? This general study of Darboux, he does not have these equations. Really, has the number of roots is 2, 3, but these equations and inequalities are very, very handy when you want to study bifurcation problems. Here are our first and second fundamental forms that you write in terms of these functions, and then in terms of this equation, that is this equation here is the same as this, written in form of determinant. I will not have time to talk about the bifurcations, the Darboxian umbilics. Again, the fact that the Darboxian umbilics discovered by Darboux, studied by Darboux, without him knowing, these are the characterized the points which are umbilic and at the same time are structurally stable. No? The Darboxian umbilics are those which are structurally stable. And then Darboxian umbilics are those which in the lifting that I was mentioned, the Lee-Cartan lifting, you have hyperbolic singularities of vector fields. No? And now here we have the theorem of Gutierrez and myself, which the condition D is the condition of my subject, which is the condition that the limit set. Now it is more clear that than before, that here you have lines, they distribute and they move in this surface, and you have singularities and you have periodic orbits. And then all the conditions are Darboxian the first time, the conditions of stability. All the umbilic points are Darboxian of type D, 1, 2, or 3. All the principal cycles are the type H. H is a hyperbolic, means that the return map is a hyperbolic map. And in geometrical terms, this can be proved, this hyperbolicity condition can be proved, can be expressed in terms of this integral involving the mean curvature and the Gaussian curvature of the surface. So really, which depend on the, so, and here we reach to the last condition concerning the lines of curvature and the possibility of not respecting this condition. these are the recurrence. No? This is the condition of Peixoto for absence of recurrence orbits for a vector field to be structurally stable. And here appears again this condition that we impose again. So the theorem of Gutierrez and myself says that the class defined by these four conditions is open in the C3 topology at least, and dense in the C2 topology. So this condition C2 and C3 is not a corollary of Peixoto's theorem, but it is involves many of the techniques developed by Peixoto and then improved by Puig and also by Gutierrez to study the closing lemma. So this is why the class of density is C2. And so where are the recurrences? So the condition says that you don't have recurrence, and densely, for a dense system of surfaces, you can avoid the recurrence. You can eliminate recurrence. No? But so in the papers that we published with Gutierrez, there are examples of recurrence, and the new examples, the examples of the double torus. So this is, you have to control. No? The problem with these systems is that you have to control the surface. No? If you want to produce a recurrence, you don't want to produce a recurrence in one place. You don't want to make recurrent in other place also. It is the same thing that you have in dynamical systems, except here that is more elusive than dynamical systems. So thank you very much for